In your notes it says permutations with restrictions grouping, just because we already talked about one kind of question is a permutation with a restriction. Those were the spaces where if you had a restriction you dealt with it first. I don't want to confuse those two ideas, so we're just going to call this a grouping question. So what we're going to look at is what happens when you want to group certain objects together but still arrange them. And I've got a formula here. We're going to come back to this page. We're going to first look at an example. Okay? I want to arrange all my math books. And I happen to have 4 calculus books, all different, 5 algebra books, all different, and 4 geometry books, all different. So the first thing that you're going to find with grouping questions is sometimes people will get grouping questions and identical objects questions mixed up. You have to ask yourself, are they identical, the 4 calculus books, or would they be 4 different calculus books? And I probably should even have worded it better in this question by saying 4 different calculus books. But chances are I wouldn't have 4 of the same book. Makes sense? So I want to arrange them on my shelf in a row, but I want to keep the calculus books together, I want to keep the algebra books together, and I want to keep the geometry books together. So with a grouping question like this, you think of it in sort of 2 different stages. Or in some ways you can think of it as decisions. We've got more than one decision that we have to make. First, I need to decide, am I going to have my calculus books first? Or am I going to have my algebra books first? How am I going to arrange the different groups? So decision number 1 is my groups. How many groups do I have? I have 3 of them. How many ways could you arrange 3 groups? 3 factorial ways. Calculus, algebra, geometry, calculus, geometry, algebra. Algebra, geometry, calculus, algebra, calculus, geometry. Geometry, calculus, algebra, geometry, algebra, calculus. 6 ways. Then, once I've decided how many groups, my next decision is to go to one of my groups, let's say my calculus group, and say, now I need to arrange my calculus books. How many calculus books do I have? 4. How many ways could you arrange 4 books? 4 factorial ways. Next decision, my algebra books. How many algebra books do I have? 5. How many ways could you arrange 5 algebra books? 5 factorial ways. And finally, my geometry books. There's 4 of them. Could be arranged in 4 factorial ways. So now that we've done this example, if we go back a slide, if objects are grouped together, we always do however many groups you have factorial first, then look at each individual group and arrange them. This is a new strategy. Our textbook hadn't had any questions where things needed to be grouped together. So we got 5 people. Amy, Bill, Jill, Lee, and Tom are sitting on a park bench. It's springtime. How many ways can they be seated if Jill and Bill want to sit together? Aww. So if we're thinking about this, this becomes, we've got Jill and Bill and Amy, Lee, and Tom. It's a grouping question because these 2 want to be together. And then there's 3 other single people. So we have to decide, where is the Jill Bill going to sit? Do you ever do that with friends? where if they're like always together, you just start calling them one thing, the Jill Bill. Or we had, I remember in when I was in high school or just first year university, there was this couple that were always together. His name was Derek, her name was Carrie. And so first of all, we need to decide how we're going to arrange this. Jill Bill first, Jill Bill in the middle. Where's the Jill Bill going to be? We have, for our first decision, the number of groups. And this is where we could easily make a mistake, because some people will say there's two groups, Jill Bill and the rest. But the rest don't have to stay together, do they? Jill Bill could sit in between them. So each of these individuals are their own group. So we have 1, 2, 3, 4 groups. Or you could think of it, how many ways could you rearrange 4 people on the bench if the Jill Bill is one person now? It would be 4 factorial. Okay? But then when you look into each individual groups, right, we have a Jill Bill, but it could also be a Bill Jill. Right? They could be holding left hand, right hand, or right hand, left hand, depending on which way they're seated. And they would still be together. So in the Jill Bill group, they could be arranged in 2 factorial ways, because there's 2 of them. And then the rest of the groups being singles, you wouldn't have to do anything with that. If you wanted to do Amy 1 factorial, Tom 1 factorial, Lee 1 factorial, you could, but it's not going to change your answer. So when we multiply this out, we get 48 ways. Part B. Uh-oh. Poor Tom. Don't worry. Tom gets his revenge in part 3. Anyways, now we have Jill and Bill and Lee and Amy have to sit together. So we've got Jill and Bill as a group, Lee and Amy as a group, and poor Tom all by himself, but still comes and sits on the park bench. It's just a really awkward hour. Okay. How many groups do we have now? 3. Then looking at each group separately, there's the Jill Bill group. Okay, that would be 2 factorial. The Lamey group, another 2 factorial. And then Tom, you wouldn't have to show it, but it would be 1. So this would be 6 times 2 times 2. 24 ways. Are you ready for part C? Something happened. Not saying Tom was involved, but it might be. But now, Jill and Bill must not sit together. Okay? Okay? We're not worried about Lee and Amy. They're sort of on again, off again. They could sit together or not sit together. It's not a big deal. But whatever happens, Jill and Bill must not sit together. And so I think I have it written out for you as the not strategy. Sometimes it's easier to count the opposite than it is to count something directly. The opposite of not sitting together would be Jill and Bill sitting together. And we already counted that in part A, right? The not strategy says if we count all the permutations, which with 5 people, no restrictions, no groupings, would be 5 factorial, 120 ways. And then we subtract the bad ones. This is where Jill and Bill are together, which we did in part A, 48 ways. If we subtract them, we would be left with the number of ways that Jill and Bill do not sit together. Does that make sense? If you tried to count it directly, It's possible, but really time-consuming and hard. You could say, okay, maybe Jill was in the first seat, but then it can't be Bill in the second, but then Bill could be in the third or the fourth or fifth. So you could sort of deal with restrictions. But then you were like, oh, but Jill doesn't have to be in the first one. Maybe Jill's in the second seat. Well, then Bill's not in the first or third, he's in the fourth or fifth. And you could go through all of those different scenarios and count them all up separately. But it would take a really long time. So if you can find the bad ones, then you'll be able to count it easier. Which gets us to our last topic of permutations. Permutations with cases. Sometimes you can't count it all at once. And I was just talking about if you wanted to count Jill and Bill directly, you could do case 1 where she sits in the first one, case 2 where she sits in the second chair, case 3 where she's in the third, the fourth, the fifth, and try to count them all separately and then figure out what you have in the end. That's an example of permutations with cases. When you can't count something all at once, you break it up into smaller parts that you can count and then add it all up in the end. A very typical one comes with numbers. How many numbers of at most 3 different digits? So you could have 3 different digits, 2 different digits, or 1. I want to say different digit, but if you have 1 digit, I don't know how it's different from itself. And 1 digit. Well, the way that we set up a cases question is when we realize we can't count it all at once, and we have to do it in cases, we write case 1 and describe what we're counting. Case 1, I want to count a 3-digit number. And in counting our 3-digit number, we'd have 3 decisions. There would be a restriction. We can't start with a 0, otherwise it would be a 2-digit number. So we only have 9 choices here. Then we can put the 0 back in, but one of the numbers is used up to give us 9 choices left. Now 2 of the numbers have been used up, so we would only have 8 choices left for 648. Case 2, we haven't counted 2-digit numbers. Again, there's a restriction. Can't start with a 0. 9 choices. Then put the 0 back in, but 1's gone. 9 left for 81. And finally, case 3. A 1-digit number. And now we get into arguments. Is there any restrictions on this one? Is 0 a 1-digit number? Or is 0 not a 1-digit number? I see some saying yeah, some saying no. Is 0 a number? Does it have any digits? I think it does. So in this case, I would argue that you could include 0 here and put 10. And then with a cases question, if you've counted things separately, there's no overlap in any of them, then your total is just what happens when you add them all up. So 648 plus 81 would be 729 plus 10, 739 total numbers. I think to get rid of the argument, I think in your textbook they ask a similar question, but they say between 1 and 1,000. then they don't have to argue about that 0. The other place that case questions come up are cases or questions that have restrictions, and our rule was deal with the restriction first, but sometimes you can have more than one restriction on a question. Okay? So in this example, we're looking at 3-digit numbers. We're only using 1, 2, 3, 4, 5. Repetition is not allowed. It has to be greater than 300 and even. So if I would go and draw my spaces, I have a restriction on my first digit that it can only be a 3, a 4, or a 5. I have a restriction on my last digit that it can only be a 2 or a 4. And then with restrictions, you're supposed to deal with your restriction first. But here we have 2 restrictions. Which one do we deal with first? Well, let's say I decide to deal with this one first and put a 3 here. What number do I put in there? Should this be a 1 or should it be a 2? Why should it be a 2? I didn't use the 4. How do you know I didn't use the 4? I picked any one of the 3. Right? If I didn't use the 4, it should be a 2. But if I use the 4, it should be a 1. So we have a problem. I don't know if I should put a 1 or a 2 there. Okay, so then I think, okay, well, maybe I should do the other restriction first. I should make this a 2 to begin with. What number do I put in the first one? Do you see I have a problem again? Because if I use the 2, I can put a 3. But if I use the 4, I can put a 2. And I don't know if I use the 2 or if I use the 4. And so we run into a problem. When I try to do this directly, I don't know what numbers I need to put in. In order to solve that problem, I break up one of my restrictions and do it in cases. So here's an example. So first of all, this isn't going to work for us. We can't count it directly. I pick one of my restrictions. Let's say I pick the last restriction just because it has only 2 things. And I say, case 1, I'm going to look at all the numbers that end in a 4. So then my 3 spaces, I'm saying that my last digit's a 4. One choice. I still have a restriction on my first digit. But now, how many choices would I have for my first digit? It could only be a 3 or a 5 for 2 choices. I've dealt with my restrictions. There's no restriction on my middle number, but how many choices would you have left for that middle number? 5 numbers to begin with. We used up 4. You've used up either the 3 or the 5. We'd have 3 choices left. So there would be 6 numbers that end with a 4. Now in cases, what you look at is after you're done a case, you say to yourself, what haven't I counted yet? I just counted all the numbers that ended in a 4. What haven't I counted? Case 2, all the numbers that end in a 2. 3 decisions, but now this time I'm saying it ends with a 2, one choice, and now there would be no restrictions. Well, on the first restriction, I could have 3, 4, or 5. 3 choices there. How many are left in the middle number? You've used up 2 numbers, 3 left for 9. My total, add up my cases. There's 15 numbers greater then 300 using only the numbers 1, 2, 3, 4, and 5 that are even. Not very many. I guess your other option would be to write out all the numbers from 300 to 500 and X them off or circle them if they work. I don't recommend that. That takes too long. This isn't the only way you could do this question. You could do 3 cases and start with your first restriction. Starts with a 3, starts with a 4, starts with a 5. Or you could do your first restriction and say, it's really, if I go back and look, this is my problem, the 4. So I could do a case where I start with a 3 and a 5. And I could do a case where I just start with a 4. That would also work. The idea is when you have more than one restriction, and that restriction shows up in both places, then you're going to have to count it with cases. Greater than 232. Again, this is part B. We're only using the numbers 1, 2, 3, 4, or 5. Now there's lots of restrictions. Well, if we try to do this directly, greater than 232, can you see that you could start with a 2, a 3, a 4, or a 5? Does that make sense? But then when you go to your second number, so if I put a 4 in here, when I go to my second number, this is where I'm going to run into problems. Because sometimes I could put a 1 for the second number, and sometimes I can't. Like if I picked a 5 to begin with, can you see there's no problem doing a 1 next? 510, perfect. Okay. But if I picked a 2 as my first number, I can't have a 1 as my second number, because then I'd have 210, 215. That's not bigger than 232. So these questions that are numbers that say greater are always going to be case questions. And the way that I like to systematically set up my cases is start with numbers that would guarantee that it would be bigger, right? The problem's with the 2. So if I start with a 3, a 4, or a 5, then afterwards it's going to be fine. I'm counting my numbers in the 300s, the 400s, and the 500s. There's going to be no restrictions afterwards. So I make underneath my first number showing that I'm restricting this to 3 or 4 or 5, 3 choices. Then there's no restrictions afterwards. I have 4 numbers left, then 3 numbers left. 36 ways. Case 2. I'm going to start with a 2. Then, because I want it bigger than 232, I'm going to have a problem if I pick a 3. Sometimes things work, sometimes things don't. So again, in order to guarantee that it works, after my 2, I'm going to put a 4 or 5 next. I'm going to count my numbers in the 240s and 250s. Then there's going to be no problem with what I pick as my last number. So to show that, started with a 2, 1 choice. Then I'm saying either a 4 or a 5, 2 choices. Then for my third digit, it doesn't matter, because I'm going to count numbers in the 240s and 250s. How many choices do I have left? 3 numbers left for 6. And then finally, what haven't I counted? I haven't counted any of the numbers in the 230s. So case 3, I'm going to start with a 2, one choice, then a 3, one choice, and then my last number needs to be bigger than 2. So there are restrictions on this. What choices do I have left? And this is why it's really important you write your choices underneath. Because some students say, hey, bigger than 2, that's 3, 4, or 5. And they write 3, 4, or 5. What's wrong with this? I've already used up 3. I can't have it there again. 3's gone. 3 was the middle number. So my only choices for that last digit are a 4 or a 5. 2 choices. 1 times 1 times 2 is 2. How many ways can this be done? 44 ways once we add them all up. So what's happened up till now for permutations, if we sort of summarize, right, because next is combinations in your note, yeah. So if we summarize for permutations, what we have developed is a bunch of different strategies. Strategy number 1, spaces. Make a space for each decision, and then put how many choices you have into those spaces. That's basically the fundamental counting principle. With spaces, we had questions where there were restrictions, saying that we need the number to be even. We need the number to be odd. If you only have one restriction, you dealt with your restriction first. Okay? After doing spaces and spaces with restrictions, we got to questions with identical objects. Identical objects showed up with words or names that had repetitive letters. Mississippi had lots of S's, lots of I's, lots of P's. So we divided out that identical object. Identical objects also showed up with the pathways going north, north, east, east, north, east, north. So we could solve questions like that with identical objects. So your job with identical objects is to say, is there something in this question that is exactly the same as something else? So if I switch them around, it actually isn't something new. Today we learned about grouping questions, how we can have certain people want to be together, or certain things of one type wanting to be together. You want to go home and rearrange all your PS4 games. You want to keep the sports games together and the action games together, and then you have 15 cooking games for whatever reason. How many ways could you rearrange those? That becomes a grouping question. And finally, we had cases questions that we looked at, where you can't count things all by itself. In the cases questions, the cases could come up with a restriction. And all of these could happen together or separately. Another strategy for all of these that came up was the not strategy, where sometimes it's easier to count the opposite than to count things directly. So now when we work, and the rest of the class is going to be a work period because I've given you 4 pages of permutation questions that are all mixed together. When you read a question, you have to decipher which one of these strategies is present, Sometimes I've seen 3 or 4 of the strategies all together in one question. How do you work with that? How do you come up with a logical way to count what you need to? And the best way to practice with permutations is to come across new situations, figure them out, and understand the logic. So we're going to take the rest of class to work on those homework sheets.